Great. We are moving right along, section 4.6, and we're going to talk about titrations today. And this is going to be a really useful lab technique that we will use whenever we're back in the classroom. And it's useful to help to track chemical reactions. So a titration is also known as volumetric analysis, and it's going to involve using a special device known as a burette. And we will use titrations to determine an unknown concentration of a certain analyte in a solution. Okay, so we would have a flask of a certain volume of a solution, and that solution is going to contain an analyte of an unknown concentration. So some examples that we have done in the past, we have determined the amount of acid that we have in a drink like soda or juice. And that's what we will do whenever we introduce titrations later. So the analyte would be the thing that we don't know what the concentration is that we are trying to figure out. And that would be, we would make sure that we have a known volume of it, and we will use that to determine what the concentration is once we have gone through the titration using the titrant. So we will use a titrant that has a known concentration. We will put that into a burette, and we will carefully track how much we are adding to it using that burette as we add more and more of it to the analyte solution. So we want to find what is known as the equivalence point, which is where everything that we have within our analyte solution reacts with the titrant. And we want to know when it happens. So we would use an indicator that would change color once the equivalence point was reached. So the goal is to find something that will change color at that equivalence point. All right, so the equivalence or stoichiometric point is just where all of the analyte has been consumed in the reaction with the titrant. So we are essentially making the analyte our limiting reactants by reacting with the titrant completely, but we want to know as close as we can how much titrant was needed to react with all of that analyte. Okay, so essentially what we're looking for is for all the analyte to be consumed in this reaction, but we want to make sure that we use just enough titrant to do that. So the endpoint is going to be a noticeable change in the property of our analyte. So as more titrant is being added, a lot of times titrations are done with acids and bases. So as more titrant is added, it may be becoming more acidic or more basic. So indicators are really good at showing certain ranges of pH, and ones that actually change color around the same time that the equivalence point is reached. Those are going to be our ideal indicators to show the endpoint that occurs right around where the equivalence point occurs. So it's a really nice indicator when something turns from clear to really bright pink to show us, hey, stop adding titrant. That's just enough. We don't want any more. Okay, so we are looking for the endpoint, this color change, to match up exactly or as close as possible to the equivalence point. So we need to know what the reaction is. So we really need to know what our titrant is and also what the analyte is. We just don't know how much of the analyte we actually have. So we need to be able to mark the stoichiometric point where all of the analyte has been consumed. So it's necessary for the endpoint to be right at that stoichiometric point. So we will carefully track and wait for that change. So we'll slowly add more and more and more titrant as we are stirring up the mixture of titrant and analyte until we see that change. And then at that point, we need to abruptly stop adding that titrant and then measure the amount of titrant that was added. So a very common indicator for acid and base titrations is phenolphthalein, which will be colorless as an acid. And then as it turns basic, it will, as it turns basic, it will turn pink. So if we are using a juice or a pop as our analytes, okay, that would be acidic, so it would look colorless. But as soon as we add enough of something like sodium hydroxide, then it will turn pink as the equivalence point is reached. So reactions that can be treated with titrations, we would commonly think about acid-base reactions. In fact, that is what we will be doing this year. I will do my best to also provide you with with a redox reaction titration to supplement that as well. Okay. So instead of using an acid to react with a base or a base to react with an acid, we would use a reducing agent to titrate an oxidizing substance or vice versa. And we'll talk about exactly what reducing and oxidizing means when we get to the redox reactions. So this is a setup for a titration. So we would have a ring stand, a clamp, and then a burette, which is kind of like an upside down graduated cylinder, you could say. But at the very top here, there would be an opening that we would pour our titrant into, and then we would fill it all the way up to, as close to zero as we could get. That would be our initial reading. And then we would use the stopcock down here to gradually let more and more of the titrant into our mixture. So we would be mixing until we start seeing a change in our analyte. And at that point, we want to add very small increments of titrant, which is really nice with the burette because we can turn the stopcock very slightly and it'll just let out a few drops at a time. So this is a really, really accurate way of dispensing a solution into another solution. You just got to be careful. All right. Don't turn this all the way parallel because then it's going to let it run out pretty fast. Okay. So right here, looks like we had an acidic solution with phenolphthalein in it, and then we were adding base, and now it is really, really pink, which means that it has bypassed the equivalence point now.